Okay, how y'all doing today? Today I'm excited. Today's the biggest day in the whole semester, but I want to clear up one thing first. Last time I told you that this was a hard class, didn't I? Did I say that? You all knew that? You know what you're getting into? All right, well here's the thing. I told you it was a hard class, and normally when I say that, a lot of people leave, but for some reason nobody left this time. I don't know why. It's kind of surprising. So if you're trying to add and you're here, email me, email today's code word. Today's code word is bleach. That will keep you on the mailing list. But I'm just going to tell you, if you're not a first-year student, it does not look good for you adding in. Like very few people dropped. Normally some people drop, like 5 or 6. This time 1 did. So I don't know what to tell you. If you're not a first-year student and you're trying to add in, that's not looking good. If you are a first-year student and you're trying to add in, it's also not really looking that good, unless something happens after day and people realize that I'm actually insane. You may want to make alternate plans, and I'm really sorry about this. If you look around the room, it seems like there's plenty of space, right? Doesn't it? Like maybe we should be able to fill in there. The problem is that I can't really expand the class to more than 45 people. The limitation is not seats in the classroom. It's actually the TAs and graders who are available for helping and grading assignments. So that's sort of the problem, and I apologize for that. If you're trying to get in, it's going to be tough unless something strange happens, okay? All right, hi everybody. Let me mess with the lights here. Is that a little better? Better, worse? Okay, good. All right, so I'm excited for today. Today is actually a very big day. It's an important day. It's actually the biggest day of the week for me, and do you know why? No, it's not my birthday. It's not. It's because I'm applying to teach in Italy. Anybody heard of the villa that they have in Italy for Georgetown? So I'm going to apply to teach there, and if I'm lucky, I will go to Italy for a semester and teach. I'll take my family. It'll be really cool, and you all can stay here. That's fine with me. So, or maybe I'll see you there. So I'm gonna apply to Italy. So anyway, that's just a joke. Really, no. Today is a big day in this class. It's actually the single most important class of the semester. All right? It is the most important day of class that we're going to have this year. Because today, I'm going to tell you the one most important thing you need to know about programming out of a whole semester. Okay? I'm going to tell you the one secret to programming success. The thing that far more than any other thing in the semester makes a difference to you. If you learn only one thing from this class, this is it. And if years from now I run into you on the metro downtown and I see you, which has happened, I will give you an impromptu quiz, and I will say what was the most important thing from 051. And this is it. Are you ready? Wait, there's actually one thing I have to do first, sorry. So I'm going to go teach in Italy, but I have to take my application over to the car barn. Anybody know how to get to the car barn from here? How do you get to the car barn? You're nodding, so. Wait, I'm going to write this down so I don't forget. Go down where? How do I get to 37th from here? Wait, which door do I go out of? Go out the far door. I can't actually see what I'm typing here. All right, go out the far door, then what? Walk down the stairs. Head south. That's great. I like that. Head south. And I know I'm not capitalizing things right. Statue, yeah? All right, car barred. Okay, car barn's on the right. Is that right? Does everybody sort of agree with that? Is that how you get there? Here. I like throwing it though. Anybody else? All right, so that's how we get to the car barn. All right, so sorry, let me just get back to what we were doing here. All right. And okay, so here's our big thing. Remote. Okay. And so here's a big thing. And I interrupted you to get directions to the car barn. So you're probably thinking, what the heck, Clay? You led us up to this great suspension of excitement, of BuzzFeed type headlines where you're going to learn the one thing, and then I interrupted you for what? Directions to the car barn. Why did I do that? Exactly. So what have we just done? What did we do in that interruption? Yeah? Sort of. Pseudocode expresses what? Anybody know? We've developed step-by-step instructions on how to get to the car barn. What does that have to do with programming? What does that have to do with the one secret of programming, the most important thing you need to know? Yes? Sort of, you need to be specific? Yep. An algorithm, exactly. So, what does this have to do with programming? It is an algorithm. Anybody ever heard this word? Algorithm? It's important. The most important thing you need to know about computer science is it's not about programming. Computer science as a discipline is really about algorithms. It's about algorithms. What is an algorithm? It is, we'll look at this a little more, but it's a sequence of steps taken to complete a particular task. An algorithm is a sequence of steps taken to complete a task. And here is the secret that I promised you. Okay, the one thing that you need to know, the one most important thing, is that every computer program is just an expression of an algorithm. Okay? The important thing isn't the program. The important thing is the algorithm. The important thing is, how do you take a problem and break it into a series of steps that a computer can solve? That's what the program is doing. It is expressing an algorithm. Every computer program is just an algorithm. Now, when I say that, this word just hides a lot of complexity, right? The development of the algorithm is actually one of the most important things. Now, the secret is you can't actually write a program without understanding the algorithm that you're trying to express. How many of you ever sat down to write a paper without thinking about your outline or your process? Yeah, all of you have. How did that turn out? Not well. In programming, if you sit down and you start programming without thinking of your algorithm first, you're going to have a bad day, right? It's probably not going to work unless your algorithm that you're expressing is so small you can do it on the fly. Right? Everybody good with that? So you have to develop your algorithm before you do anything. So I'm going to reinforce this even more than I have because it is very important. Okay? An algorithm is an ordered series of steps used to perform some task. Does order matter? It does, right? If I was getting directions to the car barn and you told me first to turn left at the John Carroll statue, it wouldn't make any sense because I hadn't completed the necessary steps to get to the point where it was right for me to turn left, right? It would just be confusing. So the steps have to be in order. Okay, so an algorithm is an ordered series of steps used to perform some task, and a program is an algorithm expressed two ways: in a form that a computer can execute, and in a way that humans can understand. Now, some of you had some programming before, right? Most of the time when people learn about programming, they only worry about this first part. That is the part that a computer can execute, and less about what humans can understand, but they're both important. So let's talk about both of them. So an algorithm is, a program is an algorithm expressed in a form that a computer can execute. And when we say in a form a computer can execute, we always have to specify in algorithms in terms of what the entity that is performing it is capable of doing. Right? So it doesn't do you any good to tell me how to get to the car barn by flying through the roof. Now, Superman might be able to do that, right? Superman has different capabilities than Batman, and I am not Batman, just for the record. But you can give directions in a different way. In Batman, you would have to say, look, you got to walk to the car barn, or jump out the window on your rope and get in the Batmobile and drive over there. Superman, you can just say, blast through the roof and go over that way. They have different capabilities. I can generally only walk. I could get an Uber, right? There's like different things that I am capable of doing, But whatever you tell me to do has to be specified in a way that I can do it. And what we're going to see is that when we talk about computers, and computers doing things, computers are actually incredibly limited in what they are able to do. They seem very powerful, and we'll talk about that, but what they are capable of doing is actually really very, very small things. Not very much. But they can do a lot of it. Okay, so the other part of a program is it's not only an algorithm expressed in the form a computer can execute, it's also in a form that humans can understand. And this is actually an incredibly important part. It may even be the more important part than the execution sometimes. And here's why. Programming is a team sport. In the real world, one person doesn't just sit down and write 10 million lines of code to run the space shuttle. One person doesn't sit down and write Microsoft Windows. One person doesn't sit down and really do much of anything by themselves. Except in this class and many others, we're not going to do team things. And my analogy for this is like, say you were on a basketball team. You have to learn how to dribble and shoot and pass before you can be an effective member of the team, right? You have to have individual skills to bring to the team before you can be a good contributor. So this class is kind of your individual skills class, and as you go on, you will have opportunities to do the team thing. And if you graduate and keep working in programming-related areas, you will do everything as a team. In fact, one of the modern things today is called pair programming, and a lot of people are hired to be pair programmers, 2 people sitting at one computer programming together. And the goal of this reduces mistakes, because you have someone saying, why are you doing that? What's going on? Tell me more. And so you have 2 people thinking about things, and it turns out you introduce less errors into the code that way. So what we want to do is make our code clear to humans, always. Even if it might run more slowly. Sometimes there's tricks you can do in the code that make it faster, but it makes the code less readable. We don't care about that in here, okay? We don't care about performance. And in fact, if you ever get to the point where you need to make your code run faster, you can worry about it then. Like, just write the algorithm first, get it working well, and then later go back and do any optimization if you even need to do it at all. Because computers are wicked fast, they can do a lot for you. Okay? So I'm saying this mostly for people who have programmed before. Performance doesn't matter in this class. Clean code that is readable by me and the TAs is what matters. Everybody got that? All right, so to re-summarize our important summary, a program is an expression of an algorithm. An algorithm, and to write a program, you must know what algorithm you're trying to express. You have to sit down and think about the algorithm before you can write the code. Now we're going to do some stuff that is going to make it easier for us. We might have very large algorithms that we want, that we break down into smaller pieces, and then we're able to write the smaller pieces and test them individually instead of trying to create something all at once. And occasionally, while we're building things, we will write additional code that is not useful, that we will eventually tear out and throw away. And it seems like a wasted effort to do this, but let's say we're building a building. When you're building a building, do you only bring in the building materials and put them right where they're supposed to go and build the building? What else do you have? Have what? Well, cement's a building material. What else? Scaffolding. That's exactly the answer I was looking for. You have scaffolding. So when you're writing your programs, as we'll talk about later, you can add scaffolding to your programs and then remove it when you're done. Okay, so you don't have to make everything perfect at once. You can design an algorithm, write a program, and you can put stuff in the program that is not part of the final product and just pull it out when you have the final product working. Okay, I wonder where I'm going with this. All right, so the other thing I mentioned before is that computers are really limited in what they can do. In fact, they're incredibly limited in what they can do. Right? But, so what can computers do then in the hardware part? Anybody know what computer hardware does? Yep. What does it store in memory? What does it store in memory? You're right, it stores things in memory, it gets it out. Okay, files, any other answers? Yes, sir. Okay, what kind of input does it read? Okay, yep. It also, but what's it working on internally? It takes input, it stores it. What is it actually working on inside there? Only one thing, numbers. Everything in the computer is stored as a number. Now, as we're going to see, it's stored as a binary number instead of like a decimal 10 number like we're used to. But all the computer can do is deal with numbers. That's it. Now, we've touched on some of the things already, really, and when we do numbers, we're really talking about arithmetic. It can add, it can subtract, it can sort of multiply and divide. Most of the time it does this by twos. Okay, so it does stuff, but not very much. Math on numbers, simple arithmetic. And the other thing that computers do is they can store a lot of numbers, right? Many numbers. Numbers in numbers so large that we have a hard time actually envisaging them. So they do math, they store numbers, and when you get down to it, computers are actually really stupid. So, if they're stupid and all they can do math, how can they do all this cool stuff that we know and love? Play games, send text to our friends, make pictures disappear on Snapchat, like whatever it is. How do they do it?
Because we tell them.
We tell them to, but the real answer is they are stupid very, very fast. Computers are dumb, but they are dumb very, very fast. In fact, they are dumb unimaginably fast. Seriously, they are dumb, but they are dumb so fast that we have a hard time understanding it. So here's what I want to do to show you how dumb they are and how fast they are. We're going to have an adding competition. So what I would like you all to do is get out a pen or pencil, a piece of paper. You can use an abacus, you can use a slide rule, log tables if you have them with us. What you cannot use are any electronics. So we are going to be racing people against the computer. Does that sound fair? No, of course it's unfair. That's the whole goal, is to show you exactly how unfair it is. All right? So, everybody get ready. Here's what we're going to do. I'm going to show a number on the screen. And when I show the number on the screen, I want you to add it up. And the first person to add it up, raise their hands. Okay? I'm going to time it. Let me get out my stopwatch here. If I can find the stopwatch. And I will time how long it takes to add it up. All right, stopwatch, and winner gets some candy if they want, okay? So, don't be shy. Are you ready? Everybody ready to add numbers? All right, you're going to race against computer. On the mark, get set, go. Come on, you're losing already. All right, hand was up. So, what is your answer? Okay. Wait a minute, come on now. You can't stop the timer then. What's your answer? Shout out numbers. 475. All right, close enough. So, either you or I made an addition mistake. There you go. All right, so that took 18 seconds. 18 seconds to add up numbers. Were those numbers pretty big? Yeah, not for a computer. Those are well in the range of computers. So let's take a look at something here really fast. Let's look at a comparison of how, this is really challenging. Okay, it took, let's call it 18 seconds to enter the numbers. Well, a computer can add approximately 2.7 billion numbers a second on one core and one processor. Okay? Just adding. About that many operations a second. So it takes the computer roughly 3.7 times 10 to the minus 10th seconds to add a number. We're on the order of fractions of a nanosecond there. So the computer is approximately 48.6 billion times faster than a human. 48.6 billion times faster. Now, can you even conceptualize how big that number is? The answer is not very easily, okay? So let's look on this other spreadsheet. So if we look, a computer can add, using that 18-second mark we did before, a computer add as many numbers in 1 second as you can in 1,540 years. Now, if you eat and sleep instead of just adding continuously for 1,560 years, it will take you about 4,620 years to add up as many numbers as one core on one processor on one computer can. A laptop, nothing fancy. And my laptop has 4 cores, so it can go 4 times as fast as this. So in 1 second, one core on one computer can use up 60 of your lifetimes, just adding numbers. Is that a huge number or what? I mean, it's almost, it's just inconceivable. Going back to prehistoric times, if one person spent all their time adding numbers, the computer would have done that in 1 second. And that would have been a fraction of what a real computer can actually do. So the takeaway of this is what? Computers are dumb, but they are dumb what? Very, very fast, like insanely fast. Like so fast, it's just almost impossible to conceive how fast they are. All right, so this is incredible, right? We have made a machine that can do something with information so much faster than we can do it. So much faster than we are even close to being capable of doing it. So it's almost impossible to imagine. So by comparison, as a rough estimate, a human runner can run the 100 meters in about 9.58 seconds. My slide's a couple years old. I mean, it might be less than this now, but not by much. If you can imagine the equivalent of a computer running it, billions of times faster, if computers could run proportionally as fast, they would run about 8.1 million kilometers in that, in that time. All right? And if you do that work, that's about 2,820 times the speed of light. So it's not even physically possible. Computers are so much better at doing this manipulation of the numbers we are, it's inconceivable. So that's just not a good analogy. And it's probably a bad analogy because the scale of difference between people and computers is just something that we, just as humans, cannot even understand. Computers can do a lot. People are really, really, really bad at dealing with large numbers. Right? Just really bad at it. We just don't understand it. So there's no really good comparison. Now, you can do a lot with the stupidity if you have enough of it. And even though computers are stupid and can just do math, they can do so much math, so incredible amounts of math, that you can harness this to do lots and lots of different things. If it's a problem that is solvable by computer, if it has data that can be represented by numbers, and pretty much every piece of data you can come up with can be encoded into a number somehow, and we'll talk a little bit later about how that's done. So we have so much stupidity in the computer, we can do a lot with it, and we do. We have actually more power in the computer than we can even understand. So just think about it. I mean, every second your computer is sitting there doing nothing, it's like 1,040 years of boredom for it. Right? Can you imagine how boring it is to be a computer just sitting there all the time? It'd be amazing. So, all right, so we can do a lot with it. So let's look at what we can actually do on the computer. Turns out that there's not necessarily that much. So one of the things we can do is we can start running an algorithm. If we want, we can start running an algorithm, but what's an algorithm expressed in the form the computer can understand? A program. So we can run a program, which is the same thing as running an algorithm. A program is an expression of. One more time. Program is an expression of. You can't write your program if you don't know the. Exactly. You will just get in trouble if you sit down and start coding and you don't know where you're going. Okay? Remember earlier when I talked about you're writing a paper about meerkats and all of a sudden you have honey badgers? That's because you didn't think about your algorithm enough ahead of time. Okay. So we can start running a program. We can stop running a program. As we heard earlier, we can read input. Like that's actually useful because otherwise your program will suck. It'll just do the same thing every single time if you can't provide input. It can show output, which is what makes it useful to us. Not much use in having a program that does something and that doesn't tell us what it did. Right? We don't like that. And it can perform operations. And the operations I mean are like math. It can do addition. It can do a bunch of stuff we'll see. It can make comparisons between numbers, which is really useful. Because now as our program is running along, we can actually look and say, if this number is the same as this number, do something. If it's different than this number, do something else. Right? So we don't have just to go one way. We can actually have branches and choose different things to do depending on the internal state. And that's about it. That's literally about it. We can do operation, branches, start, and stop. Now, some of the operations are sending and retrieving things from memory and disk, but that's it. And we can do this all very, 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 very fast. All right, I've been talking now for 24 minutes. 1 minute break in place, go.
But I was still told that because I started after the classes started, I need to fulfill up forms.
Okay, send me an email. And I'll look and see. Okay, you need to send me an email and I'll check and see if you're actually added to the course or not. So. Okay, welcome back. Do you all feel better after your big break there? Yes, no. Show of hands, who likes little breaks? Show of hands, who doesn't? Because it disturbs your coma, daydreams. Okay. So we can't actually do much, right? We can start programs, stop programs, we can send things to and from memory, we can do operations, and that's not much. Now the good news is that computer programmers are lazy. But we're lazy in a good way. And the good way that we're lazy is we like to not have to recreate things over and over again. So when somebody hands you a computer, they don't just hand you hardware that can only add up numbers really quickly. They also give you software that a lot of other programmers have worked on a long time to make it more convenient for you to use. Does that make sense? So as we program things, we're going to be building upon the work of other people who have provided us an interface that has a lot of code that does stupid stuff very fast behind it that makes our life easier. Okay, so we don't actually have to start from scratch. Now you can think of all these different things that they've provided as sub-algorithms that you can use. When you have your algorithm, you don't have to just think, add a number, move a number to disk or memory, bring it back. You can actually think in terms of the pieces that other people have worked out for you. And this is a really good model. All the programming and all the work that we do as computer scientists is almost always based on a lot of other stuff. Like in cases, thousands of years of human hours of work, just tons and tons of work, so much work. Okay. So when we're working, you can use other people's sub-algorithms, or you can create your own kind of sub-algorithm. So if you have some sort of piece that you want to reuse over and over again, we'll see how to do that. You can develop an algorithm that does one thing, like compute a square root, or move an image on a screen, or detect whether a projectile in a game has impacted something else, right? There's all sorts of algorithms you use, and once you've written that algorithm, you can use it over and over again. And that's very, very good. So the question is, if there's only a certain number of things that a computer can do, how do we represent this in a way that we can think about it easily? Right? How do we do that? Well, the easiest way is a flowchart. And the flowchart is like the primordial representation of an algorithm that crawled out of the swamp 50 million years ago, and then my analogy fails, but it's very primordial, right? Flowchart is the easiest way you can do this. Anybody ever worked with flowcharts before? You ever seen them? Okay, so you're pretty familiar with them, okay? So, things we can do with a flowchart. We can start. This tells us where to start our algorithm. Now the thing about flowcharts is they are called flowcharts because they allow you to follow the flow of the algorithm. They allow you to show what steps are in sequence by following the lines that are attached to the individual objects. All right? So you start somewhere, you follow the line. You have a little trapezoid. This is generally the flowchart indication that you're doing some input. And there's actually a lot of these symbols for flowcharting that are computer science and programming specific. In fact, when I was a kid, my granddad had a big stencil that had all these different symbols on, because back in the day when computers were expensive and filled up a room, you actually had to draw your entire program as a flowchart and then have somebody else read through it to make sure it was correct before you could put it on the computer, because computer time was so expensive that they couldn't waste it on programs that were not likely to succeed. Nowadays, computer time is so incredibly cheap, we don't necessarily need to do that, but it's still useful to think about our algorithms this way. So we have input. We have this rectangle, which means we can do an operation. Oftentimes, this is like math or addition or things like that. The useful thing we talked about before is we can make a decision. And the decision is always a decision that has a yes or no output. Are these numbers equal? Is one bigger than the other? Is the other smaller than the one? Is something true or false? Right? Anything that you can get down to a yes or no is a decision. So that's part of our flowcharting. And then we have the ability to do output. Output also uses the same trapezoid shape as input. And then finally, we can stop. This is literally all the operations that a computer can do. All of them. Now, when I say all of them, there's a lot that goes into this, right? When I say operation, there's a number of different things. Down at the lowest level, these operations are all just math that the computer does. In the language, they're often calls to kind of sub-algorithms for something that you do often. So let's talk about that. What do you do if you do something often in your algorithm, right? Like let's say that you're going to get a list of people that all have some characteristics and you want to figure out something about each person. In your flowchart, do you actually have to have compute this for person 1, compute this for person 2, compute this for person 3, all the way through with the right number of people you have there? Yep, exactly. If we don't want to do this extra work and copy it over and over, right? Remember, programmers are, but we're lazy in a good way. I have a 9-year-old child, and it drives my wife crazy. I am teaching him that. So he comes home with things, and it's like they give him a big sheet of squares, and they're like, cut out the squares and put a shape together and name it. He cut out one square, glued it in the middle, and said, it's a square. And I was so happy. I was like, that is like the laziest thing you could possibly do to get things done. So I don't like doing extra work. Engineer training, I'll just tell you, engineers are trained to do things so that they are just barely good enough, right? Now you set the standards good enough very high, but there's no point in going way past the standards. Once you get just barely good enough, you stop there. As you can tell by my teaching style, right? So just barely good enough. So what we want to do in our algorithms, we have something, we don't want to copy things over and over, right? It's extra work. So what we can do is we can design a sub-algorithm. And for a sub-algorithm, we can take kind of any combination of things before. And what you see there is kind of the entirety of what I had on the board before. We have an input, an operation, a decision, and output. And what we're doing is we're saying this box that has these extra lines in it for the sub-algorithm represent all those operations in one. And then if we replace everything, that's the same flowchart we had before, except now we've replaced all the internal things with this sub-algorithm. When we get to programming, these things are going to be called functions. These sub-algorithms will be called functions or methods in different contexts, but we will be writing a number of these sub-algorithms at different times. But the idea is we have one big algorithm. When the algorithm runs, it has one thing that's known as the flow of control. That is, it goes step by step by step. It essentially follows that line, and it does everything in the algorithm until it reaches stop, and then it stops. Okay. All right, so how will we use flowcharts in this class? Do you want to know? We really won't. Okay, we'll do a couple of problems with them just to kind of get used to how they're doing, but they're very useful to kind of envision the flow of an algorithm. If in your mind, at any point when you're thinking about an algorithm or program, you think, I don't quite know what's going on, just go, well, what would this look like as a flowchart? And where would the flow of control be going through these operations so I know what's going on? Sometimes one of the things people get confused on is when they're looking at programs is like how to do things in order and what the order is. Okay. All right, so algorithms are a series of ordered steps. The flowchart makes that flow very explicit. Right, you have to follow the little line everywhere. All right, everybody good so far? Any questions, by the way? Feel free to ask me questions while we're talking, while I'm talking. 17-second rules in effect. 15, 10, 2, 1, 0. Okay, 17 seconds is up. Any questions? All right. So that's one way. This flowchart is one way that we can make the order explicit. How else could we do this? You had a great answer earlier. What was your answer? Pseudocode. So when we're coding a program, coding and programming are kind of used interchangeably. A program consists of code, so coding is creating a program that has code in it. One of the things you can do is you can do what's called pseudocode. And pseudocode is just kind of an expression of an algorithm using other statements that are not like explicitly for the computer, but people can understand very well and you can use to reason about what you're doing. The simplest way to do this is just to use an outline. Anybody ever worked with an outline before? Right? We like outlines. So an outline will consist of essentially these steps, right? Input, output, calculate, decide, start, stop. And you can use this language to figure out different things. Okay. So here's a little algorithm. Who wants to tell me what this does? Yeah? Yes, this is we're going to be talking about algorithms. Algorithm is a series of ordered steps, and we're going to be representing these algorithms in different ways. The simplest way is a flowchart, because you can actually visualize this little line running around everywhere. The outline is another way of doing it. It doesn't have the little line, but what we're going to do is we're going to start and just go down line by line. Okay? And then later, we will get to how to do this in C++, which is a programming language. Programs exist just to implement algorithms. So this is kind of in between. Okay, so everybody's good with this idea of like flowing through the flowchart, right? When we have an outline, what happens is we start at the top and we go down line by line by line. We just go from top to bottom. Now occasionally, later on in the semester, we'll see one of these things where a decide box actually makes us go back up here, right? But we will always be reading these things line by line as we go down. Same thing with computer code. Computer code, when it's an expression of an algorithm, and the algorithm starts at the top and goes step by step all the way down. So start, input, what's the input going to say? Tell me a number. What number do you want to give it? I heard someone say 6. Okay, divide the number by 2. What's 6 divided by 2? How long does it take the computer to do that? Fractions of a nanosecond, right? Really, particularly dividing by 2, that's like one of the fastest operations a computer can do. All right, decide, is the remainder 1 when you divide 6 by 2? Okay, no. So do we do the if so or if not? If not, right? Because we decided that this is no, so it's not true, so we get if not. So do we output? Even. Was our program correct? It did. Okay, just so you know, this this algorithm expressed as a C++ program is something that people use for programming interviews. Like if you ever go to a programming interview, the first thing they might ask you is, write me a program that tells if something's even or odd, and they do that to filter out people who are completely incompetent. Okay? So after we see the program version of this, which will probably be next class, you will be able to get through the first step of a programming interview, and you will not fail until after that. So. Okay, but that's a good start, right? I mean, only like 3 days of class and you can get past the first question. All right, so this outline which we just used right here is what you will do on the homework, okay? And the homework is posted on Snapchat, and when you look at it, you'll have 2 seconds to read it, okay, before it goes away. Actually, I'm kidding. It's actually on Blackboard, and just so you know, between us, I'm not a big social media person, so throughout the semester, I will occasionally refer to Facebook. And when I say Facebook, you should go, Clay, dude, you mean Blackboard, okay? So I might even call it Faceboard on occasion. So if you go to Blackboard for this class, even if you're on the wait list, you have been added to the Blackboard roster. So you should be able to see this. It actually just points to my web page, and the project's posted on my web page. So the homework is due in 1 week from today. It's due as a PDF file submitted through Blackboard. Okay, and it's going to be thinking about things. So we're going to use this language. We'll use this kind of step-by-step language to think about a couple of problems, just to get used to the idea of working with algorithms before we program. All right. The other thing we're going to do is we're going to use this input, output, calculate, decide, start, and stop on design documents for a couple of the projects. For the first part of the semester, we're going to have 5 programming projects. First two, you will be required to turn in an outline form of the algorithm that your program is going to do. Okay? Before you actually program. Why do I do this? Yeah. Yes, so you actually have to think. Now, the cruelest thing that I do is not to make you do the design documents. The cruelest thing that I do is I don't make you do them for the other three projects. And why is that cruel? Nope, that's not cruel. Yeah? Because they're helpful. Here's what's going to happen, right? The first two projects, you're going to have 2 weeks to do the projects. The first two projects, the design document is due after the first week. So you're going to spend the first week thinking about your algorithm, writing it down, and you'll spend the second week writing the code. When you get to project 3, here's what's going to happen. You're going to have 2 weeks, and you're going to start the project when? Tuesday night before it's due, probably at about 10:30 at night, I'm guessing, knowing students, and you will not have spent time thinking about your algorithm. And instead, here's what you're going to do. You're going to go, oh my God, I have to write a program. I should start writing a program. And you'll just sit there and you'll start typing code. And at about 2:30 in the morning, you're going to go, oh, this just isn't working. What's going on here? And the problem is not going to be in the code. It's going to be in the fact that you haven't written an algorithm and that you're tired and sleepy and just not thinking very clearly, and you just never wrote your algorithm, and you're stuck. Okay. So I would encourage you, even though I'm only making you do it on the first two, to do some sort of thinking about the algorithm before you write ahead of time. Otherwise, you're going to get in trouble. And like I said, I've taught this class a lot, and typically 1 or 2 people come up after project 3 and they're like, I did really bad and I'm so sorry. And I'm like, oh, which brings up one other thing, by the way. I don't judge you as students on the basis of your grades. In fact, I actually don't care what your grades are to a large degree. I care that they're fair and I care that you get credit for what you're doing. But if you get something you think is a bad grade, it doesn't really affect how I think about you. Okay? You're all people, you're all individuals. I respect curiosity and engagement much more than I respect high grades. In fact, I don't really care about grades. Okay? So even if you think you've screwed up and done bad or something, you can come see me. It's not going to change my opinion about you. I will still be happy to help you and stuff. Okay? Okay. I have no idea what I'm talking about because I just went off on like 4 tangents. So, okay. So we're going to do design docs. Okay. So if we're using this outline stuff in order to do our algorithm, what are we going to use for the programs? Anybody know? Have I told you? C++. Okay? We're going to use the C++ computer language in this class. Now, C++ is a language that will allow us to represent an algorithm in a way that the computer can understand. You will write in a language that is human understandable, and you will use a special tool called a compiler. And the compiler will take this semi-structured human language and it will turn it into a binary language that is all just numbers, because remember, what does a computer work with? Nothing but numbers, right? It'll turn it into numbers that make the computer run. In fact, even the instructions that the computer have to do are turned into numbers. So, yep.
For the outlines, are we going to be handwriting them, or is there an official?
You can handwrite them as long as you turn them into a PDF file. You can take a picture. You can type them. I'd type them just because I'm lazy. And my handwriting is really bad, as you will learn later in the semester if I ever have to write things on the board. Yes, sir? Okay. So the question is, do you need a compiler for every computer language? And the answer is no. There are a variety of computer language. This is what's called a compiled language. If you ever use something like Python, it is what is known as an interpreted language. So in a compiled language, as we'll see, you write all your code, you give it to the compiler messes it up into code that the computer can run, and the computer will run it, and you'll test it. In an interpreted language, you can actually do 1 line of code at a time, and the interpreter figures out what to do for that line. So there's a whole menagerie of programming languages. Okay. All right, so this compiler turns human-readable code in C++ into a computer executable. All right, everybody good with that? So your job is going to be to come up with an algorithm, write code, and then run it through the compiler and stuff. And let's look at the actual process you'll have to use to do that. How's that sound? So here's what you have to look forward to when you write code. So this is the algorithm for completing the projects. What's the first thing you think you're going to see on the algorithm? What? Start? Who said start? Start is correct. The first thing you're going to see, start. But there's some special kind of start for our projects. What is it? Said so last time. 3 most important things for passing the class. Start early, right? So start early. You want a piece of candy? I feel like I'm not throwing this out enough today. Anyone else? Okay, start early. In this class, you need to start early. Why do you have to start early? So you have time to get help if you get stuck. Okay? Start early, you will have time to get help. It will make you happy. So the first thing you're going to do is read the problem. Each programming assignment is going to have a problem. It's going to be something that's relatively related to the real world. After you've read the problem, you're going to design an algorithm that will allow you to solve that problem. Okay? The algorithm has to take those steps: input, output, calculate, start, stop, decide. Once you've designed the algorithm, you're going to express that algorithm into C++ code. So you will design the algorithm however you want, and then you'll write it in C++. Right? Once it's done in C++, you will feed your code to the compiler. And the compiler will look at your code, and what will it say about your code? Yeah, it's going to say, pretty much, not in this language, it's going to say, you suck, try again, okay? The compiler is not very friendly. And the compiler will tell you if there are errors. If there are errors, you need to go back and re-edit your C++ code until there are no longer errors. So remember earlier I said occasionally we will see decisions that take us back in our list. Here's one of them. So edit the code, compile. If there are errors, go back and re-edit your C++ code until there are no longer errors. At that point, we've reached this no, errors no. Are you done? You are not done. Just because your code gets by the compiler doesn't mean it's correct. Your code passing the compiler is kind of like Microsoft Word not underlining any grammar errors. Okay? Could you sit in Microsoft Word and just type random stuff in there and have no grammar errors? You could. You could absolutely do that. It would have no grammar errors. It would be correct, but your writing would still suck. Okay? So when you do this, when there's no errors, you have to run your test and you have to make sure that you do not have errors in your algorithm. This testing is actually a big part. There's like a whole area of computer science dedicated to how do you test things? How do you test software? How do you test hardware? How do you detect errors in them? Okay, if as a result of running your test, your algorithm design is incorrect, you get to go back to the point where you design your algorithm. You make changes to your algorithm, you edit the C++ code, you compile it, you've probably introduced some bugs, so you go through this a little while, and then when you think you have it right, you go back to running more tests and see if you have accidentally confused meerkats with honey badgers, right? This is kind of where this goes wrong, where your algorithm's not right. And then eventually it will be correct. At that point, you will submit your code for grading. Now, this semester we're going to try and use an auto grader, which is a program that tests your program. So it's possible that when you submit it to the auto grader will barf and say bad things about your code, in which case you might have to go back and do some other stuff. But in general, after you're done, you're all done until next week. Okay, so this algorithm is literally how you should approach the projects. And you'll see me doing a lot of this stuff in class. When we get into coding, I will actually be standing up there typing on my laptop. I will be coding in front of you. I will be designing the algorithm, editing the code, compiling the errors. You'll see me do all this stuff. The reason I do that, instead of just flashing up slides of beautiful, perfect code, is because you don't actually learn much from seeing perfect code. You learn a lot more from watching me make mistakes. It'll help you learn how to fix your mistakes. And I promise you I will make mistakes. It just happens. Okay. So here's what we've talked about today. We've talked about algorithms. We've talked about a couple of different slide off. Sorry. We've talked about algorithms. We've talked about a couple of different ways to represent them. We have given you an algorithm for you to use when it comes time for you to program. there's nothing left for us to do except start looking at how to represent our algorithms in C++. Are you all ready for that? Okay. And we're going to talk about computers work in really, really deep detail. That's it for right now. Okay. So right now there's one other thing I want to do. In this class, we will on occasion take a little break from our normal routine of listening to me talk and do some problem solving in class. And the way we're going to do that, I'm handing out a handout about it right now. It's called partner assisted problem solving. So I'll hand these to you. You have a 1 minute break in place to hand these out, and when we come back, we will talk about how to do this partner assisted stuff, okay? Oops, sorry. Let me also hand these out. These are a little bit of problems. So I'll pass these back. You should have two-sided sheets there. Oops, sorry about that. All right, so while these are going around, let's talk about this partner-assisted problem solving. One of the things I have learned as a professor is that the very best way to get a student to solve a problem is to have them describe it to me. Anybody ever had the experience of having a problem and like going to ask a professor or a teacher about it, and you get there and they say, "What's your problem?" And then you say, "Oh, well, I was working on this thing and I realized that." And then the other thing, and while you're talking through it, all of a sudden you realize your mistake and you solve the problem. Anybody ever had that experience? It is really, really super common, okay? As I talked about earlier, a lot of computer companies have people do what's called pair programming for the same reason. If you were sitting there and you were working through a problem with someone else, the process in your head of thinking of how to explain the problem helps you organize your thoughts and it helps you get things right, okay? So in this class, what we're going to do is some partner-assisted problem solving. From time to time, as appropriate, I will pull out a set of problems. Instead of having a 1 minute stand-up break, you will scoot your chairs around to find a partner, and you will do this partner-assisted thing. So you will have two roles. Typically, there will be two problems so that each of you can solve at once. But here's what you're going to do. You will split into groups of two. If we have an odd number, we will split one group into three. In the group, you will have stuff to solve the problem, typically a copy of the problem, something to write with, something to write on. For the problem solver, you're going to attempt to solve the problem. But the way that you are going to solve the problem is not just solving the problem in silence while people sit there judging you. Okay? That is not the point of the exercise. The point of the exercise is for you to explain your thought process as you solve the problem. So as you're going along, you will start. And the steps for this are here. We have a nice little algorithm here. Step 1, look at the hints or suggestions if there are any given. I generally don't give hints or suggestions because I'm a jerk. Okay, you figure it out yourself. Step 2, and this is important, read the problem out loud. Read the problem out loud. Step 3, if you find that you have not read the problem out loud and you both and the partner just sat there silently, go back and read the problem out loud. Okay? The fact that you are speaking the problem actually helps your brain remember the problem. It helps to read it out loud. Okay? Step 4, you will think out loud as you solve the problem. This is not easy. We are not used to sitting there going, okay, we've got a pie plate and we have a blueberry pie and there's a fox and a chicken and a bag of corn and we have to take it over the river and all we have is a bulldozer, right? So you have all this stuff and so you have to think and you're like, all right, well, you know, the chicken can't drive the bulldozer, so we have to have a pie there. I mean, whatever the logic is, you just go talking it out. And your goal and your job is to think out loud. When you're going along and you get stuck, and you might get stuck, you go, I'm not sure about that. I think I need to go back. Okay? So you will explain what your thought process is as you're going along. The other thing to do is try and solve the problem even if it is trivial. Like if it's something that's easy for you, it may be beneficial for your partner to listen to your thought process, right? So if I gave you, what's 3 plus 7, you might go, well, 3 plus 7, that's pretty easy. And I go, well, if I take 7 fingers and I take 3 more fingers, now I have 10 fingers, right? I taught my son to count that way. He's quite good at it now. He knows that if you just give him any 2 numbers, he will, like if I say, what's 112 plus 8, he'll go 113, 14, 15, 16, 17, 18, 19. He'll know it's 121. I just totally screwed that up, didn't I? Anyway, okay, he's much better at it than I am. So that's the algorithm. So, okay, so it's useful to do this stuff out loud. All right. The listener, on the other hand, is not there to assist the problem solver. They're not there to give them the answers. They're there to just get them feedback on their thought process. So as the listener, it's really important that at first you don't just go, you're doing it wrong, you suck, right? Wrong answer. Just go, why do you think that? Is there another way you could solve it? Are you sure that's right? You were just there to ask questions to provoke them into being clear about their thought process. Okay? Does that make sense? That's it. So don't interrupt them. Make sure that they're talking. If they're not talking, say, hey, what are you thinking? Why don't you let me know what's going on? What do you think about that? Why do you think that? Don't just sit down and solve the problem on your own. That's rude, right? You're the listener, not the solver. Oh, if you're a group of 3, you'll have 2 listeners. And don't let the problem solver just continue if they go, okay, we put the chicken and the chicken drives the bulldozer, and you're like, don't just go, wait, chicken can't drive a bulldozer. Right? That's just the worst analogy that I'm running with. But just say, wait, why do you think a chicken can drive a bulldozer? Right? Are you sure that's right? Shouldn't somebody else be driving the bulldozer? Whatever. So if you don't understand their thought process, make them clarify. If they do something wrong, don't just go, hey, that's wrong. Go, are you sure about that? Do you really think that? As you will learn if you deal with me over the course of the semester, I like asking that to people who are right. So if you ever come to me and you go, I think it's this, I'm going to go, are you sure about that? And if you're like, yeah, I'll be like, yeah, you're right. Right? I really enjoy doing that. So just because I'm asking you, are you sure, doesn't mean that it's wrong. Okay? I'm just making sure that your thought process works. And finally, don't give them hints. So here's what we're going to do now. We're going to do a practice set of problems like this. You have a sheet that has 2 problems on it. I didn't save one for myself, but is there an extra one somewhere? Pardon? Extra sheets? Why don't you pass them that way, if you don't mind, and then pass them back forward. One probably says something like a watery mess, and the other says something about a solar system. I've been using the same problems for a long time. All right, so we're going to do this. Everybody find a partner. Make yourself comfortable where you can talk to each other, rearrange your desks, scoot them together. In about 4 or 5 minutes, we're going to do... Okay, wait, listen, stop. One of you be the listener, one of you be the solver. Do the watery mess problem first. Got it? Thank you.